All right, thanks, Ali, for that wonderful introduction. So, like Ali said, I'm Matt Hinkley. I'm principal scientist at the Gatorade Sports Science Institute. So, obviously, we're going to be talking about sweat today. So, we're going to be talking about why it's important to understand someone's sweat rate and what is in that sweat, the differences between individuals as far as sweat weight, and how we can actually test this in the lab. But then, of course, I'll be talking about some data from our group and a new technology that has been released in the last couple of years that is out on the market that you yourself can actually understand not only your sweat weight, but what is in that sweat. So obviously, as far as disclosure, I work for the Gatorade Sports Science Institute, which is a part of PepsiCo, and I'll be talking about one of the products that we have on our market today. So first, I want to talk about heat balance, particularly during exercise. So I'm going to go back into my background of exercise metabolism. And when we start exercising, particularly with endurance exercise training like this runner here, we need to use the carbohydrates and the fats to fuel our activity for prolonged activity. But as many of you probably know, we are very inefficient human beings. If we were a car on the market, we would not buy ourselves. So in fact, we are about 20% efficient. What that means is that of all the energy that we bring into our system, only 20% of that is used to fuel activity. The rest of this 80%, actually is heat production. So this increase in heat production throughout the body increases core temperature. So you could only imagine that this is not helpful for performance. We also have additional stress factors that increase this core temperature, including solar and diffuse radiation right from the sun. We also have other environmental factors, including reflective radiation, conduction through the ground, and convection through the air that we run through, as well as the type of clothing and the evaporative resistance. So if it's more humid, we're less likely to lose sweat that way. It stays on our bodies. So if we look at all these different factors, all these are related to an increase in heat, internal heat within the body. So we need some mechanisms that will allow us to release that heat, to bring us back to more of a homeostatic environment. And that's through evaporative sweat. This is our main way of losing heat, particularly with exercise. So everyone's probably seen a picture of this where someone is exercising and just dripping with sweat. And this is very important, as we know, to lose this heat. But it's very important about the amount of sweat we lose as far as how it relates to fluid balance. Because as many of us know, we are about 60% water. And this body water is important for many different functions throughout the body, including the nervous system function, blood volume, and blood pressure regulation, the transport of oxygen and nutrients throughout the body, so it'll help to fuel that activity while we're exercising. Of course, heat transfer and waste excretion. So small changes in the amount of body fluid throughout the body can have drastic effects on whole body physiology. Now, we always think about the amount of fluid that we're losing through exercise as a main driver of performance loss or heat balance, but we also need to take into account what is in that sweat. There are many different molecules that are found throughout sweat, most notably electrolytes such as sodium and chloride. But there's also trace minerals such as calcium, potassium, magnesium, zinc that can be lost in sweat as well. And I like to focus on sodium in particular and its importance because, as we know, sodium has many physiological roles, including stimulation of thirst, of course, fluid and electrolyte balance, fluid retention, so the ability of keeping water into our system, and of course, cardiovascular function. So again, very similar to changes in body fluid, small changes in sodium concentration throughout the body can have drastic effects on many different physiological systems that are important not only for overall health, but for athletic performance. So if we look at the idea of hydration physiology and exercise performance, if there's a state where we lose body fluids, this is called hypohydration. So we are not bringing enough fluid in while we're also losing fluid at the same time. This leads to two conditions called hypovolemia, so a lowering of plasma volume, so loss of body fluid, as well as hyperosmolality, which means basically the concentration of your fluids has more concentration of sodium chloride, which is also not a great thing as well. And all these together can lead to many different physiological changes, including cardiovascular strain, increase in body core temperature, increased muscle glycogen utilization, and of course, an increase in fatigue. Now, collectively, all these together, as we know as exercise physiologists, are crucial for exercise performance. So how does a hypohydration state lead to a decrease in exercise performance, or does it? And this is actually shown here in this paper by Stuart Schifron and colleagues in 2014. And what they looked at is the level of dehydration and how many individuals showed a decreased performance in an endurance exercise event. So we look at just a 2% body mass loss. So very similarly, if it's like a 100-pound person, they go down to 98 pounds during exercise. They observed that 14 out of 26 people of observations that showed 2% loss had an impaired performance. And as you can see, as we increase the level of dehydration from 2 all the way to 7, there's a greater prevalence of performance impairments, at least with endurance exercise performance. And this is also shown in more of an anaerobic or high-intensity exercise as well. So we know globally that being hypohydrated or dehydrated can have a severe impact on performance. Now, this has led to guidelines through various organizations to help prevent hypohydration, particularly to prevent this greater than 2% body mass loss from water loss during exercise. You also, while you want to drink while exercising, you don't want to drink too much where you gain weight. This could lead to conditions such as hyponatremia or low levels of sodium in your body fluids. And along with body fluids, you also should consume sodium with fluid if large sweat sodium losses occur, which is greater than 2 to 3 grams. And this could occur with prolonged exercise, so very similar to Ben when he was doing the New York City Marathon. So if you're going 1 to 2 hours, if you are have a high sweating rate, which would be over 1.5 liters per hour, or if you're just a salty sweater. These all things could be considered to having sodium in your drink or in your food while you're exercising. So these are just guidelines in general for everybody to use. So, when we hear about like carbohydrate utilization during exercise, there's always that 30 to 60 grams per hour that's known for endurance exercise. But we don't really have that with hydration. And the main reason behind that is that everyone is different. Kind of like what Ben was saying with the glucose monitor, that you can't have one person who sweats a certain way and another person will sweat the same way if they do the same exercise. And that's actually shown from a paper from the GSSI team a few years ago, where they studied the sweating rate of over 1,000 athletes and looked at the variability in sweat rate response to exercise. And this was a broad range of individuals from 9 to 70 years of age, from 23 kilograms all the way up to 178 kilograms. And it also was in various temperatures, including as low as 11 degrees Celsius all the way to 50 degrees Celsius, and either low or high humidity, as well as low and high exercise duration. And as you can see, the average sweat rate for individuals is around 1.1 liters per hour. But as you can see, it's greatly variable, where you have individuals who only sweat 0.5 liters per hour. And then you have some people who are high sweat rates in the range of 3.5 liters per hour. So think about that. In 1 hour, these people can lose 3.5 liters of water. So that's why guidelines has to be have a personalized effect for a person, because just saying, hey, go out and drink a liter of water may not be beneficial for someone who is sweating so high, or may not be as beneficial for someone who's a low sweater. So why is there this variability in sweat? There's many different factors that could be involved with this, including exercise intensity, a person's body size, so someone smaller may have a different sweat rate than someone larger, like an NFL player. Air temperature can obviously play an effect, as we mentioned in the first couple of slides, as well as clothing and equipment. So having, think about, summer camp for football, where they have all the equipment on and they haven't maybe been training as well, it may not be beneficial to, as far as affecting their sweat rate. Their fitness level is very similar to that, someone with a low fitness in comparison to someone with a high fitness. And of course, heat acclimation. So training and heat, understanding what it's like. We just had the Boston Marathon this past Monday where it was a little bit hotter than people were probably thinking that the marathon was going to be. So many individuals found it harder and probably had different sweat rates because of this reason. And of course, other factors can play involvement in this sweating rate. So we talked about the one arm of how much fluid we're losing. Now about how much sodium or electrolytes someone is losing. Does this follow a similar trend? And actually, it's very similar, where there's a lot of variability in the amount of sodium that is lost from people that could lose just 1 gram per hour up to people who could lose 2 grams per hour. So what are some of the main drivers of this differences in sodium loss with sweating? So we have to go back into the physiology of sweat. And we really will focus in on the exocrine gland, which is the main ubiquitous gland throughout the body that's involved with sweat. So everywhere that you sweat throughout the body is mostly driven by exocrine. And for this, the exocrine glands, there's a secretion of precursor fluid by the secretory coil in response to a local release acetylcholine. And then from there, there's a reabsorption of sodium and chloride in the duct, and that's shown on the figure on the left, where we have an isotonic sweat, and then once it goes through the duct, it gets reabsorbed into the body, leaving a hypotonic solution. So we'll focus on the duct here and how this can be adapted either acutely or chronically. So chronically, the effects on sweat composition are driven by 2 different systems. The sodium-potassium pump, which is affected by aldosterone, and this could be impacted both by heat acclimation and dietary sodium. So if you exercise in the heat for prolonged periods of time and you become adapted to it, the activity of this pump can change, as well as dietary sodium. So if you change how much sodium you take into the diet or not, it can affect the pump activity. I'm glad that's over with. The other receptor that is involved in this pump is the CFTR, and this is influenced by genetics. So if you know someone who has cystic fibrosis, this is actually what is involved with cystic fibrosis, and actually a hallmark of cystic fibrosis is a greater amount of chloride in sweat. So this is more the chronic sense of what can be done to alter sodium and chloride sweat. Now, acutely, it's really dictated by the amount of sweat that's flowing through the system. So we could literally look at this in an acute exercise sense, so after one bout of exercise. So this was a study that was done a few years ago that looked at the effects of different exercise intensities. So they did an exercise at a heart rate max of 50% all the way up to 90% of their heart rate max. And they looked at how this affects the amount of sodium that's found in sweat. So as you could imagine, as you increase exercise intensity, you increase the amount of sweat rate, so the amount of fluid that you're losing. And in this case as well, there's an increased amount of sweat sodium that is in that sweat. So not only are you sweating more, but you're losing more electrolytes. And on the opposite side of it, we look at the reabsorption into the system from the duct. There's a decrease of reabsorption of sodium as we increase sweat rate as a context of an increased exercise intensity. So globally, factors that influence variation in sweat sodium include exercise intensity, and this is more the acute sense where we get a change of 175% increase in sodium sweat by going from a 50% heart rate max all the way to a 90% heart rate max. Heat acclimation, so training in the heat or being in the heat for 7 to 10 days can chronically affect the amount of sodium that you lose, including a 30 to 60% decrease in the amount of sodium that's lost in sweat. And then, as I said before, dietary sodium can also affect the amount of sodium that's in sweat. So obviously, if you're eating more sodium will be lost. In contrast, if you're taking in less sodium will be lost. So this has led to more fluid replacement guidelines by the National Athletic Trainers Association as well as ACSM. So I'll read a couple of these. So first, they suggest quantify sweat rates during exercise in various environments. Develop fluid replacement practices that promote sufficient but not excessive hydration before, during, and after physical activity. And for ACSM, the goal is to prevent excessive dehydration and excessive changes in electrolyte balance because there's considerable variability in sweating rates and sweat electrolyte content between individuals. Customized fluid replacement programs are recommended. So as you can see here, 2 major organizations are suggesting more personalized approach for hydration. And in fact, the National Athletic Training Association says you need to quantify sweat rates to understand what you need to put in. So how's this done? How do we quantify sweat rates? So the standard sweat testing procedure goes like this. If we want to look at a whole body approach as far as changes in sweat rate, we can look at differences in body mass before and after exercise, while accounting for how much fluid someone takes in, as well as how much someone urinates as well. We can also quantify what's the composition of that sweat by collecting that sweat. And there are 2 different methods that are commonly used in the laboratory for this. The first is at the whole body level. This is the whole body washdown method. And basically, if you first indication, what does that mean? It's exactly what it says. Like, basically, you wash the person down, you collect everything that they have sweated out, and then you analyze that sweat to see how much electrolytes are in that sample. However, we've come a little bit further down to now looking at regional differences in sweat rates. So this could be done by either having someone's hand in a bag and collecting the sweat that comes off the arm, or with this absorbent patch, as shown here, so a small region. And then from there, we could take this sweat either from the whole body level or from the regional level, and then we could look at the analysis through using a high-performance liquid chromatography system, or HPLC, which allows us to measure the amount of electrolytes as well as other minerals in sweat samples. So as you could only imagine, doing the whole body approach may not be the most economically or easy way to do this, and that's why we have now gone to more this regional approach. So the question is, what is the best site to look at? And this is actually done by a study from the GSSI team, where they looked at various different sites at the front of the body as well as the back of the body. And they compared this to the whole body sweat rate response as shown here. So the results are shown here. So on the x-axis, we either have the whole body sweat rate, or on the graph on the left, or our sweat sodium loss on the right, with the white bars being a low intensity and the black bars being a moderate intensity exercise. And as you can see, with exercise, there's an increase in either sweat rate or sodium loss, as shown before. But if we look at the variability between sites from the whole body to using the 11-site approach, which means all 11 sites that we tested in lab, there's considerable difference when we look at either the wrist, the calf, if we look at the triceps, and of course, if we look at the forehead. Both for sweat rate as far as sodium loss, there's a lot of differences between the sites. So what our team did was correlate the differences between the regional as well as the whole body to see which sites can give us a more precise approach to understand someone's sweat loss. So if it's a practitioner in the field, we say, put the sweat patch on X site. So for this, we want to make sure there's a high correlation between whole body and regional sweat sodium, sweat chloride, and sweat rate. So here's the results that we have here. And as you can see, all these were significant positive correlations between these, but we wanted to have a number that was closest to 1. And from there, we saw that the upper arm, as well as the dorsal forearm and the ventral forearm, provided the highest correlation between the regional, this area, to whole body sweat rate. So if anyone in this area, in this room here, is interested in looking at sweat rates in their athletes, we highly recommend using these regions. Now, this symposium is about personalized hydration and monitoring. And of course, we talked about continuous glucose monitoring before as a novel way of wearable technology to understand nutrition for athletes or the type 1 diabetic. And as we know, understanding sweat and sweat rate response is very important for understanding hydration status. But not everyone in this room here can collect a sweat sample and run it on an HPLC to understand the sweat concentrations. So with this in mind, the GSSI team developed a new technology that the everyday user could use to understand their sweat rate, as well as their electrolyte content in their sweat. And this is through the GX patch. So we took the knowledge that we gained from sweat loss through changes in body mass, fluid and food intake, as well as urine loss. We took the knowledge that we had from sweat electrolyte concentrations with using the different techniques I mentioned before with ion chromatography. We took the technical expertise, interpretation, and recommendations based off our knowledge and as far as other organizations' knowledge, and we funneled those all into a sweat patch that we have here that uses a smartphone app to help you understand the everyday user how much someone sweats, as well as the concentration of that sweat. So first, I'll focus on the GX app in itself. So this patch, it uses microfluidics. So essentially what that is that it uses the known pressure of the exocrine sweat gland to divert that sweat into two different microchannels. The first microchannel that we have here, the sweat combines with a orange dye, and then it goes through this channel. And this allows us to measure the local sweating rate with this patch. So the further it goes down, the higher the sweat rate. The next channel that we have, this microchannel 2, it combines with a silver chloronylate. And when those two combine together, gives a estimate concentration of chloride in that sample. And that's actually shown here with different amounts of chloride. As you can see, from 25 millimole all the way up to 100 millimole, there's a progressive increase of that color, or that purple color. And this allows us to measure the amount of chloride in that sweat sample. Now, as I mentioned before, there's a lot more data of the importance of sodium. So why are we measuring chloride in the sample? Well, one of the major reasons is actually the assay to look at sodium in a sample is very unstable. So it's really hard to do. And in fact, there's no colorimetric assay that can be used to measure sodium. But if we look at the correlations between whole body chloride and whole body sodium, there's actually a strong positive correlation with an R squared of 0.98 between chloride loss as well as sodium loss. So chloride can be used along with regression modeling to understand how much sodium is lost in sweat. So we have various papers from our group that really delved into how this GX app, or this GX patch works in comparison to the known measures of hydration, as well as known sweat technologies, including the absorbent patch. And this is one of the papers from Scientific Advances that was published just a few years ago. So we've studied this GX app from competitive athletes, from high school athletes, all the way up to professional athletes. We actually tested this in G League players. We've also looked at it in more of the weekend warriors. So we tested both in the lab with people just exercising on the bike, as well as exercising in the environment. So we've done many different ways to see, does this GX app actually provide a good metric of hydration status or sweat rate and sodium loss in comparison to our known methods. So one of the things that we realized with the use of the app is that many different variables need to go into understanding someone's sweat rate. As we talked about before, when someone uses this app, they need to identify how much body mass they are, their biological sex, the air temperature, sport, exercise duration, and energy expenditure. And I'll go back to the reasons for that later on, actually in the next slide. So the first question that we had is, does the GX patch compare to the standard methods? So these are the results of the 4 different clinical studies that our team has looked at, and we correlated sweat rate and sweat chloride concentrations in the GX app and compared it to the absorbent patch that I mentioned before. And as you can see, there were strong positive correlations in all these studies as far as sweat rate and sweat chloride concentration, meaning that what we can get in the lab, we can get in this micro lab that everyone can use. We then use regression modeling to understand, can we predict whole body sweat rate and see how it compares to actual measured effect. So if you focus on the graph on the right, we looked at the predicted whole body sweat rate of chloride and compared it to the measured amount of sweat lost. And as you can see, the R-square was, so 86% of the chloride lost that we saw in the patch was able to predict the whole body. So we can actually use a simple linear regression to calculate regional sweat rate here in chloride and relate it to the whole body approach. Now, when we did the same thing with sweat rate, we actually saw that the measured sweat rate that we look at in the app only account for 50 to 60% of the variation, the prediction of sweating rate, whole body sweat rate. So, but when we took those other factors into account, including exercise intensity, air temperature, body temperature, sex, we were able to actually have this down to 72%. So taking these into account into the app allows us to more accurately determine someone's sweat rate based off the sweat patch. So how this works is that we have our GX app, and this is a personalized app that's found not only on Apple phones, but as well as Android now as well. And you can actually connect this to other fitness apps, including Garmin, Strava, or Apple Health. And from there, after you exercise, you simply just take a picture of the app. And then from there, we can provide a profile of your sweat, including how much fluid loss that you had, your sweat rate, and your sodium loss. And this can actually allow you to provide recommendations that if you do this at same type of exercise in the same type of environment, it can provide how much fluid that you should take next time, as well as the amount of sodium that you should intake during that exercise bout. So from a practical standpoint, we can think of two individuals that are both 70 kilograms, and they both exercise for 90 minutes. We have athlete A. As you can see here from the app, we can get that they lost 2.3 liters of sweat, with the total amount of sodium loss being 70 millimoles, which total being 3.6 grams of total sodium. Now for athlete B, same size, same exercise bout, they may only lose 0.8 liters with sweat sodium concentrations of being 20 millimole. And then, of course, being 0.3 grams of total sodium lost. So if we just went off recommendations on size alone, we were basically doing an in-service to both athletes if we give one recommendation. By using the GX app, this more personalized hydration, we can say for this person that they need to drink at least 1 liter of fluid to prevent this 2% loss, and up to 2.3 liters of fluid to maintain body mass. And we also provide the recommendation that it would be good to have sodium in the form of fluids or gels during this time. And then for athlete B, we could just say they may not need to take in any fluids to avoid this 2% hypohydration in the first 90 minutes. But they could drink up to 0.8 liters, so 800 milliliters of fluid, and preferably not even sodium. So you can see how it's very important to find a personalized approach to help someone in their hydration needs. So as far as the evolution of sweat testing, we have gone from measuring this in the lab from the whole body level, going to putting an arm in a bag to collect all the sweat in the arm, to now going to an absorbent patch, to now to a point where you all can go to Dick's Sporting Goods today, buy the app, buy the sweat patch, download the app, and you're able to have basically the lab that we have up in Valhalla on your forearm to measure the amount of sweat you lose, as well as the amount of electrolytes that you lose in your sweat sample. So this could help you improve your performance or your athlete's performance to prevent this hypohydrated state. So I'd like to thank you for your time and attention, and happy to take any questions afterwards.